I will let me read. So two things. One, I'm gonna I threw in a couple of chat in the chat box already. Gavin had a couple of links to some articles that he's written on this topic as well. So they're in the chat box for everybody to jump on. And then one more, I just sent out an email as well. But if anybody's looking for a virtual conference or virtual PDHs, Arizona's putting on their conference this week, and it happens to be virtual. So you could still jump on that one. That's a great conference. So you got time. It's Thursday, Friday, and Saturday this week. There is a CFED component to it as well. So those that need CFEDs, you can obviously jump on there as well. But tonight, I love Gavin's bio. It's short and simple. I love it. Gavin is a licensed surveyor, technology writer, and an administrator of a cooperative real-time GNSS network and consulting editor for Go Geomatics, trade publication focused on geomatic sciences. He's also worked in surveying, mapping, geodesy, monitoring, geospatial data management, GNSS radio navigation, and GIS for over 3 decades in the public works, commercial development, defense, and utilities. And so we've had Gavin on before. Week 68 was the last time Gavin was on, and we did some RTK topic back then. And so this one's more GNSS corrections. And I appreciate your time as always, Gavin, and I will turn it over to you, sir.
Cool. Well, I feel funny because most of the topics are about boundary and principles and things. So this is an oddball one. So
never.
This is like switching over to a UHF channel. Okay. A lot of us are old enough to remember that. So I keep getting asked to write articles on this same subject, and I operated a real-time network for about 20 years, and I get a lot of questions about the corrections that a network puts up, but also all of the other correction types, because it is the Wild West. There is a boom in correction services. There are all kinds coming out of the, mostly for the autonomy market. Everybody's jockeying for who's going to be the correction service for the autonomy market and robotics and things like that. But what's revealed about all of those is very few of them would actually be called survey grade, yet they have strengths in resiliency and availability. So there's an upside and a downside to those. So anyhow, correction services. This means any external corrections that you can apply to your GNSS receiver to improve the resultant position. And it comes in lots of different ways. So in one of the articles I linked, I put there's a summary of the different types of correction services. And I'm going to be going through most of these this afternoon or evening. But it's to note that there's other kinds. It's like the assisted GPS. Your phone isn't just doing purely uncorrected. There's a couple of different ways they handle that. They handle it through pushing a little bit of clock in orbit to you, using ranging from the cellular towers. There's all kinds of things they throw into these packages that, if the phone was totally uncorrected without a cell service, it'd be extremely crappy because the antenna is crappy. The old saying is, which pocket is your phone in, but there's some dinosaur ones, DGPS, which is still used by some people. There's SBAS, satellite-based augmentation, which is mostly a type of PPP, but there are regional SBAS all over the world. Europe has it. We have WAS over the North America. Every region of the world has some kind of SBAS, which it just can get you down to the meter. That's the whole goal. And then RTK and network RTK are the bread and butter of the surveying correction, type of corrections. but PPP is edging in there. And in a lot of cases, that can be a really good option if you don't have availability of the others. And then there's fast PPK because, well, I'll explain how PPK works and you'll see why the fast is becoming popular. So DGPS, you know, a lot of us can remember, oh, the L1 days GPS only, and then differential GPS broadcast out by like Coast Guard beacons. There was NDGPS, you know, some inland towers that the federal government finally retired those. But it's the beacon. It's the old beacon thing. The goal was to get you sub-meter on a reliable basis for the NDGPS, and they experimented with it, high accuracy NDGPS, which is to get you, you know, decimeter. But DGPS, farmers used it, mappers used it, even surveyors used it for just rough, you know, finding things or extremely rural boundaries or whatever. And in a best case scenario, you could get a decimeter out of it in the right conditions. But they're pretty much, that's gone by the wayside because there's other good ways to do this. So like I said, there's still Coast Guard beacons out there. There's, you know, the Coast Guard, there's still a great need for that kind of thing, although they're turning to other stuff, you know, maritime industry. Okay, single base RTK, that's the one that we're familiar with, and that in a lot of ways that is about as precise as you're going to get with GNSS. Short of extremely long campaign post-processing. There is, as a side note, don't let me get sidetracked too much, there are motion engines that can use GNSS like we use for structural monitoring on dams, which is half of my day job, where we're down to millimeters because it's processing over a period of time and the conditions are very well known and other factors. But when you're talking about the, you know, quote unquote centimeter, your single base RTK is where it's at. That is double differencing from multiple satellites with a base at a known point, and you're kind of modeling the corrections in one direction only. It's just that between you and the base. And so it can degrade over distance, and it does. And I can show you an example where, you know, it can really degrade over distance, but, and you're counting on the conditions being pretty much the same all the way between you and the base. So it's just modeling that one, well, I don't want to use the term vector in the wrong way, that one course. So I'm going to explain why that can be the best, you know, why, you know, technical wise, that can be the best that you can get for real time. Network RTK, RTN, VRS, MAX, whatever. Believe me, there's no real difference between the different flavors. Well, there's some subtle ones, but they, in general, what it does is you're either doing the modeling on board, getting subsets of the observations from a group of stations like a master auxiliary, or you're doing a virtual base, which, contrary to salespeople's bickerings decades ago, you actually do have a physical base in the message. So most field software, you can export vectors, not from the virtual, but from the physical base to put them into post-processing, but I digress. You're gathering observations from multiple stations, and from that, you're doing the modeling, what your single base would model for the value of the corrections, but it's doing it from in multiple directions. So you're kind of making you could call it a real-time topographic map of the correction values. There's another kind, the tilt correction, the FKP, which is a big long German word that I've never been able to pronounce, but it works pretty good, where you're sending a definition of the model to somebody, and then it interpolates where it is in that model. So, but it's all basically the same thing. You're modeling, and that can have advantages in longer baseline lengths. The stations don't have to be as close together. That was a whole impetus for building network RTK was, okay, RTK is great, but unless you put them 10 kilometers apart on different days and different iono values, you're not going to be able to get the consistency. A network will genericize that, and it can actually model out bad iono days quite a bit better than single base, but can't beat it in the short range. If your base is near you, you can see it on the site. You're shooting fish in a rain barrel, and that's as good as you can get. And I'm a network operator, and for certain things, I will recommend that that's what people do. The whole subject of drones, if I got time at the end, there's about 5 different ways that the drone operators are using GNSS in their solutions. But anyhow, I get asked about this a lot, and there's a lot of confusion. The users aren't sure which flavor to use. We have to put out about 5 flavors of correction from our network and from each individual station. And mainly it's because some people have older equipment, but it's evolved over time. Corrections. So back in the 1990s, when RTK, I think the first commercial RTK was 1996, you had to be able to send a correction from a base. And at the time, there wasn't a standard, the RTCM. It came out in the late 1990s. Around about the same time, and just before it, there were some proprietary ones from the manufacturers. An example of this, and there's a lot of them, but the examples I'm using are some really common ones that users of our network need, ask about or need to connect to. So the Radio Technical Committee for Maritime, international body, the Coast Guard's involved in it and all kinds of entities. They came out with an RTCM 1.0 correction flavor. And the problem with it was a really large packet and really rough on radios. And it was GPS only because everything was GPS only back then. At that time, GLONASS really, what's the technical term for it? It totally sucked. It got better and now it's kind of plateaued, but that's another subject. There were proprietary versions that were compressed corrections, which were better for radios. You didn't burn your radio out with the corrections. You either could go to slower rate or use a compressed version. This is a little bit of trivia. You know that in the days when machine control for radios, they would run every 2 seconds instead of every 1 second, and it didn't hurt their solution because the stuff that changes between epochs in GNSS is not that dramatic over a period of time. You got to go a couple of seconds before you start to get a degradation or enough of a change. And that's why you can transmit at 1 hertz, even 2, and the rovers can process and make solutions every 10th of a second, every 20th of a second. There's even applications for every 100th of a second. The only time you would want to transmit at a higher rate, like 50 hertz or 100 hertz, is if you have a moving base. An example of that is maritime use, or you have a platform in the ocean where the base is moving as well as the rover. So you do the high rate to get the relative between the two if you're going to land a rocket on a platform. And that's actually what they are doing. So I digressed. Then RTCM 2.3 came around, which could start to carry GPS and GLONASS, more signals. It was a large packet. It did have a DGPS message that was quite handy. So a lot of the Bugs and Bunny GIS folks, with the handhelds, they needed RTCM 2.3. That was it. Well, it's big bandwidth, really rough for radios. I go back to CMR. CMR by itself was generic, compressed. It was originally proprietary, but then they made it an open standard. So there are still users out there with equipment that can only use plain CMR. So I have to keep mount points for them. Oh God. But RTCM 2.3, that message, GPS and GLONASS though, at the same time, flavor of like CMR and some other commercial ones came out, which was the same thing, but compressed. So then it was viable for radios, and cellular was a little tougher back then. We didn't have the, we didn't, 1XRTT and 1G and stuff like that. You didn't want to eat a lot of bandwidth. So CMR Plus is proprietary, but it got so widely adopted because of the OEM market. It's, I don't know, quasi open. There's a lot of users that's all they can use. So a lot of networks have to offer that or stuff from that era. Well, in the 2010s, along came RTCM 3.1. This is pretty much the most used one in a lot of networks. And, people working over radios that aren't using a proprietary, one. And it was different. It could pass corrections and observations. And that came in real handy for lots of things like master auxiliary or exchanging data streams between stations, like the PVO stations, all those UNAVCO ones, the 900 on the West Coast. They can put out RTCM 3.1 and other outfits can use them for creating their own corrections or use the corrections. It was a better reduced packet than the earlier RTCM, was a little more friendly for radios. But again, at the same time, the CMR Plus and stuff like that was compressed, came out to help with the radios. Well, just in the past 10 years, RTCM 3.2 MSM, multi-signal message is that suffix. And what I tell users is if you have a rover that's made within the last 5 years, and you want to use all the constellations and all the signals in those constellations, got to pick RTCM 3.2 MSM or a commercial one like CMRX. Users, they force a habit. They keep using the old formats, and they call me up and they get upset. How come I'm not using as many satellites when I connect? Got to use the MSM. That is where we're at now. And there's rovers that are 7, 8 years old that can use that. Although they could be a whole different subject, is unless a rover's built in the past, like 5 years, it can see all those satellites, but it can't use them in solution for a lot of reasons. A lot of the signals are newer than that, weren't incorporated, and a lot of the old processors were too weak, but I won't go. So now there's a new RTCM 3.4 MSM. If it's available, use it. If you have a rover that can use the previous MSM, it can use 3.4. There wasn't enough of a fundamental change that would stop you from using it. So, and there's other proprietary formats that are similar patterns to this in the growth. I just say that for most people, if they use an RTCM, everything's peachy keen. There's not, well, I shouldn't say that. It might upset some salespeople, but no really significant effective difference if you use a proprietary version. except maybe a little compression for your radio, etc. So
Hey,
now,
Gavin,
yeah,
sorry, there's one in the chat that goes with this. Do I need a newer radio in order to use these newer formats?
no,
Okay.
no. If the radio is using a proprietary protocol for transmitting, though, newer ones can handle all the RTCM just fine. But there were some older radio pairs that were set up with a proprietary protocol, which made them very efficient, but they kind of choke on the newer correction formats. It may be that you have an old radio pair that has this proprietary, yeah, and you can tell because it's a buzz name for the format, that can only be paired up with a proprietary older correction type. And I see in the chat box CMRX or RTCM 3.4.
I was about to ask that same question, which obviously, because you say CMRX is same as above with compression. So if you
Yeah.
had if you had your choice, which one should you be using, I guess?
Oh boy, I'm not going to do this, or I'll
Okay.
have salespeople
No,
that'll
you're
get really
fine.
pissed off. I'll put it
Understood.
this way.
Yep.
I'll put it this way. From all of our users and all of my own testing and talking to other networks, and even people within some private manufacturing firms, that you are not going to see any significant difference in performance, except there are some specialty applications that these are better designed, the proprietary are better designed for. Running around with your rover isn't one of them. They're serving a lot of other things in agriculture, machine control, and other applications. You are going to be getting a slightly better compression with the proprietary. So if you're working with radios, as there's no difference, you may want to go that route.
Okay.
I hope I got away with that.
No, I think you did fine.
Okay.
You did good.
But yeah, if it's available, use it, you know.
Pat says, "Toed the line with that
Toed the
one."
line with that one. No, I was trying not to toe a line. I was trying to walk away from the line. Okay, now RTK and network RTK, you know, we get the whole thing about double differencing and, you know, all of that. You're reducing the sources of error in the clock, the orbit, the ionosphere, the troposphere through various modeling. Well, PPP, precise point positioning, has been around for 30 years, invented by pretty much by Natural Resources Canada, and they invented it because Canada is mind-bogglingly freaking huge. And you know, going out and doing big static campaigns and post-processing against known points, what if there's no known points within a decent range? You can't put up bases all over the place in parts of Canada. PPP can work with just the clock and orbit and regional ionospheric models. There's global ionospheric models. So PPP, it was designed for post-processing initially and has been used for about 30 years. And it's pretty astounding that, you know, hey, if you want to get down to a foot or something out there in the middle of nowhere in Nunavut, you're going to be able to do it with PPP. Well, it didn't take long for the maritime industry to come along, like with Fugro and Veripos and other maritime services outfits to go, you know what, this is real good for when you're out in the ocean or doing marine construction or, you know, near shore. And they put up their own networks of tracking stations and refined things really well and built really good clocks and orbits and added in a little bit better iono models and started offering that up in real time. And the way they do the real time is they get the clocks and orbits and they create the clock and orbit products or just the right subsets to minimize the bandwidth in the iono models, and they pump it up to a satellite and then pump it down to the user. So commercial ones, I will be mentioning a whole bunch of them towards the end, to be fair to everybody. Some of the earliest ones were the Fugro, the Veripos, the RTX, stuff like that. Well, with their own global tracking networks that they could monitor really well and create products, some of these companies started creating products that were better than what the IGS in the public entity ones were creating, a lot better. And the precision got a lot tighter, but PPP has a big Achilles heel. It needs to converge. And then when the first real-time PPP came around, we were converging for hours to get down to a sub-decimeter. Well, as things improved, the convergence got down to 12 minutes, 10 minutes, 8 minutes. Really, that's actually pretty viable. Once you have converged, and you're in the middle of nowhere, you got no cell, you got no network, you don't want to put a base up because a bear is going to eat it or something, or the person watching it. You can go out there, and once you've converged with the PPP and you've got that communication satellite in view, you can go out and keep surveying to that same precision. A lot of these are 2 to 5 centimeter, the top end ones, which is not that bad for the middle of nowhere. 2 horizontal, 5 vertical. Well, if you're on a known point with like an ITRF position handy, you can actually initialize without converging, and off you go. Well, for surveyors, they started to do some interesting things. They started to provide the same big manufacturers that sell network software and a lot of your rovers built these networks, and they provide PPP service. But what they do in the engine and positioning engine in the rover is they're running that in the RTK at the same time, if the RTK or network RTK is available at the same time. So you have a known position, you've got a pretty tight position that at any time, if I lose that cell, the PPP can take over instantly and off you go. Now, if you grab the PPP or it grabs it and you don't have view of that satellite, you got 2 to 5 minutes and you can still maintain the precision. Some of the commercial providers, as a little sales feature, they add on, they have where, it's set up to do that you've got this fill-in thing that happens if you lose your cell or you have a gap in it. That can come in handy. I won't editorialize on whether these are great or not, or whether people should use them or not. They are available, which is really great. And multiple manufacturers have this same kind of thing, this kind of fill-in thing, for gaps in your cell. But the Achilles heel of that satellite, these commercial providers are using L-band satellites that are up over the equator, like 6 or 7 of them around the Earth. So to use that real-time PPP, you have to have that dang thing in view. Or in view at least enough of the time that you can maintain your convergence. Well, the next one after this, which isn't as precise, but it solves the Achilles heel, is Galileo as the E6. Galileo's got like 6 usable signals in it. We got L1, L2, and I think 60% of the US satellites have L5 on it, which is good stuff. Michael Schroeder wants to chime in about PPP. Let him take over.
Yeah, thanks, Gavin. So I'm an old timer using it back. GPS and when we had 4 satellites, but in the late 90s, I was doing aerial sensor positioning, and Nav Canada would just release their clock you could get the clock corrections and the rapid orbit, and then that, like you said, that regional ionosphere model. So we're not doing it real time, but I was really curious about that because, you know, we're in Alaska where high latitudes, you could never see these equatorial based satellites for transmission. But it was friggin' amazing because I tested it on, you know, NGS monuments, just let it run. Every epoch had its own clock correction and the ephemeris put into it and the orbits. And it was definitely decimeter. So then I started playing with it because we're doing airplanes, high dynamic, you know, losing lock with wing bank and stuff, you know, cycle slips. And then as I had a Planex systems, I started sticking in filter parameters so we could go anywhere in the world, whether it was Barrow, Alaska, up at 71 degrees north of the jungles of Colombia, no ground control. I mean, we're not real time, right? We're doing a post process, but it was amazing. It was like freaking magic. So, you know, I guess my heart goes out to that early PPP that, you know, that's what you need. And then you deal with the world of trying to get it to everybody real time, or everybody does, all these manufacturers. So anyway, I just want to share that old gray hair story, and I'll shut up now.
No, I appreciate it. And I'm from the same era. Actually, I predate GPS. It was Doppler only, but early PPP blew me away. And like you said, it wasn't real time, but it was real good, is what we used to say. Well, actually, so, you know, the commercial PPP services that use the L-band satellites, they got these things up over the equator and you can't really see them in the northern latitudes over the whole Earth. But you can, if you have internet connection, you can pull in those clock and orbit and IONO products in real time and use it anywhere in the world. So that's pretty cool. Now, Japan had a brilliant idea. They put satellites up in that highly elliptical orbit. It's like a lazy figure eight that goes over Japan and down over Australia. And people that work in those areas are really lucky because the quasi satellites, QZSS, do a lot of things. There's a PPP type service that comes from it. And the nice thing about the quasi orbit is at any given time, there's satellite directly above you. You know, urban canyon doesn't matter. So it's a great way to send PPP. And I kept thinking, you know, the Sirius FM satellites are highly elliptical orbits. They're figure eight. Boy, it'd be great to buy a channel on that and push PPP down from that, but I digress. Well, Galileo's kind of done this. So Galileo, yeah, there's like 6 usable signals, and then E1, E5 can be used together as Altbach, which is a fantastic multipath mitigator of all things. But the E6, from the E6, they are broadcasting essentially PPP products in what they call their high accuracy service. There's going to be a closed and an open service, but the open service is holding a little bit of promise because you can get that from any Galileo satellite. You don't have to worry about those L bands over the equator. You see any of them, you can get that. And that means you can literally use it anywhere in the world in real time. It's got to converge. At this point in time, it really has to converge. There's only a handful of manufacturers that are working on implementing it right now. And some of their testing that they won't let me publish yet. 10-minute convergence time, and they're getting 10 to 20 centimeters anywhere in the world. That the mapping people are going to love this. You know, oh, there's a few rough edges and it gets a little hairy and there's outliers and all that, but that could kind of be a big part of our future if they can get the convergence time and the precision down. But it's kind of neat. So this PPP with the L band, just about any rover you buy nowadays, because of all the relationships between the manufacturers, even the bizarre off brands that use OEM in these PPP providers, is that just about any rover you've bought in the last 5 years can get that L band, the L band data. Now, whether they put it in the position engine for you or not, or want to charge you for it, that's a different, Okay, so I'm going to go through some correction services because the idea is, I guess part of the question is, could I use this for surveying? Yes, no, maybe, perhaps in the future. So these are in alphabetical order to be fair to everybody. There's Atlas. This is from Hemisphere GNSS. They're out of Scottsdale, Arizona, but I think they were owned by a big Chinese company or whatever. Hemisphere makes boards for lots of companies, including like Carlson and Bad Elf and all these. Atlas is their PPP global service delivered by L-band satellites. They sell it to you in tiered precisions, like a mapping grade, 30 centimeter, 10 centimeter, or what they call centimeter. Yeah, the Atlas Basic, which is sub-meter, 30 centimeter, 10 centimeter. I won't editorialize on which ones are better than others, but some are, and you try them out. CHC Nav, CHC out of Shanghai, but they sell in the US. They sell in our network RTK software, and which is actually a pretty good network RTK software, but they are also work with licensing PPP from others. But anyhow, yeah, they're building global RTN through network partner programs. So CNH Case New Holland, they have their AFS RTK network, which is Advanced Farming Software Network. And that's an RTK kind of hybrid. And that's for precision agriculture users. I've approached them about trying to use it for surveying, and is like, well, they're not really set up for that. They work with local farmers. They set up a lot of the social networks of bases around the heavy farming areas, and it meets the farming precisions, not quite survey precisions, but it doesn't need to. DigiFarm was another one that serves farmers, and they have a virtual base network, which is again a social network, and network RTK. They are spinning off for other high precision markets like surveying. They're not really in my state, but in the Midwest, this could be an option. I would test and see what the quality is, because I'm not in the Midwest. I haven't been able to verify, but it's just another way of doing it. eSurvey, eSurvey out of Asia there. They have GNSS net network software. Like if people have a group of stations and they want to run their own network, is one of the lower cost ones. Now Fugro, they're massive. They're a marine services company in marine construction, and they have a bigger fleet of ships than most countries in the world have navies, but they also have their own satellites. They have global PPP. They have different levels of it, different precisions, Starfix, Seastar, all these other ones. Surveying, no, not necessarily. But if you're in a remote area in different parts of the world where the other PPP won't reach, but it has marine traffic, you may be able to tap into theirs for a fee. Geo++ is a network software, like, Trimble has network software like TopCon. Geo++ is another one like that. They do a weird hybrid of PPP and network RTK. which is interesting, and the tilt correction and all kinds of stuff like that. There are parts of the US that have Geo++ run networks. Frankly, doesn't matter which brand of network of which state you're in or whatever. None is really going to outperform another. It's more of a matter of how well they run their network than the software. Now, Here Technologies, Here is an interesting company that I think they're originally out of like Finland, something to do with Nokia, the cell company. But Here is mapping the whole world, driving vehicles around. You see, these mobile mapping buggies all over the highways run by different people. It's not just Google. I've counted like 8 different ones that drive around our city. But Here is focused on creating the navigation data, the lane level navigation data for these autonomous systems. And so sometimes if you do a map of whatever navigation program you're using, it probably has Here data down in the route. But to do the lane level mapping, they came up with their own high definition GNSS, a PPP RTK solution for mass market applications, and it is solidly a decimeter or less, and you don't have convergence time. As soon as they make it publicly available, I'm going to test drive it and write an article, but that ought to be an interesting one. But it's never going to reach pure survey grade. They don't need to. That last few centimeters is a lot of expense in infrastructure. They're more spending their money on availability and reliability. High Target is another GNSS manufacturer. They have a global PPP RTK service. Again, maybe decimeter. Point one is an RTK correction service called Polaris, which if you buy something like a Bad Elf, it's one of the options you can pay for resource grade mapping out there. In some surveying applications, it can work. The IGS is the International GNSS Service, used to be International GPS Service, a federation of agencies, research entities around the world that build this tracking network where you get the IGS reference framework from, that's tied into the ITRF, which is tied into the NGS. They're all working from each other's infrastructure. And they have 400 reference stations around the world, and they've had PPP for a long time, which is free. And they have a real-time PPP service, which is free, but it's not very precise. It is not fast converging at all. Oh, about convergence time. The way the commercial PPP services, I'm going to back up. Like your SmartLink, your RTX, your TopNet Live, all of these, the way they get fast convergence is they use data from semi-dense arrays of networks. They don't have to be as close together as an RTN, the 30 to 50 to 70 kilometers. They can be a couple 100 kilometers apart, but they get them a better IONO model, and that's how you get your fast convergence. So these commercial PPP, some of them will converge in 20, 30 seconds, and then off you go. And that's called fast PPP. Well, IGS is free. It's real time through the internet, not through satellites, but you can use it almost anywhere in the world. You just got to wait for the convergence. And not quite as precise as the surveying ones, but like when Michael was talking about working in certain places, that could be okay. Like a Geosystems, they're part of that monster hexagon giant company. Those Swedes, they build big companies. They have network software, Spider. A lot of states run that. They host a lot of their own RTN, SmartNet, various regions, and they have a global PPP service called SmartLink. So they get the full boat. And their salesmen, like the others, will be very happy to tell you about all the options they want you to buy. Novatel is also part of Hexagon, and they are, you know, deep in doing GNSS stuff for their span system for IMU, GNSS, you know, kind of, and they have various tiers of PPP RTK, mainly aimed at they call RTK from the sky because it's a bit of a hybrid, sort of not, but they're targeting the autonomy market and various maritime and stuff like that. But they do have survey grade PPP like also does, and a bunch of the others. Premium positioning, there's a kind of a sort of global one, which you can use anywhere in the world, but not quite survey grade. I shouldn't say that in case they're listening, but as far as my testing has gone, test it yourself. There's RX networks. Again, they're doing a whole bunch of these different flavors for chasing the autonomy market. Now, satellite-based augmentation, I talked about that. Different, you know, EGNOS in Europe, Gagan in India, MSAS and Qs in Japan, SDCM in the Russian Federation when it works. A bunch of these other ones around the world. Australia has their own, in New Zealand, South America. It's like WASP, but somewhere else in the world. And most rovers are set up to be able to use these no matter where you are in the world. Again, if you're looking for a foot to a meter, that works. SinoComNav, they have their own course software aiming mainly at the agriculture. Swift Navigation has Skylark, which is a global a nationwide RTK in some other parts of the world, and a DGNSS service for lower precision. Again, mostly aimed at the autonomous vehicle market. And you can go and try Skylark if you want to see if it can meet your survey grade. Tersus GNSS has their advanced positioning. They're another manufacturer that isn't big in the US yet, but they've got a PPP as well. Topcon has TopNet Live. They have RTN software. Some states are TopNet in regions and stuff like that. And they host their own regional real-time network as well called TopNet. You can, when you buy a Topcon, you can pay for that. And there's your survey grade for real-time network if you're in that area. And they have PPP as well. Again, this is like, you know, your Trimbles and your Leicas and your Novatels. You do have a survey grade option in network and or PPP. Trimble, yeah, network RTN software, probably the most widely used RTN software because they kind of got into it before a lot of people. They have their own commercial network, VRS Now, in various PPP services. The survey grain one is called Centerpoint RTX. There's also a free online post-processing service through Centerpoint RTX. Be aware that when you use PPP in certain places, the NAT83 to ITRF is not exact, and you might want to, on our coast is one of the examples in the US that you might want to localize if you use a PPP, no matter whose it is. U-Blocks that make the chips that's in everybody's drones. They have their own, they're building their own PPP and hybrid for the autonomy market because that's what they're chasing mainly. Veripos, part of Hexagon, they bought Veripos, Hexagon did, and that's, again, another tiered service focused on maritime, but they're also going to be offering to everything else. And then you got Verizon that have all these cell towers, and they're leveraging all their infrastructure all over the country for a PPP RTK service well, it goes nickname of thing space. And actually, that works almost anywhere in the country. And it's the decimeter lane level type thing. Be interesting to see where that goes, because Vodafone is jumping on another cell phone company jumping into that same space. We're going to have so many of these out there. But the short of this whole list is there's only a handful of PPPs that you could call survey grade. So many of the others are chasing the autonomy market. Oh, hemisphere. Somebody just put up there. Oh yeah. John Deere still has the their star service, GNSS service, which was actually an early broadcast PPP from space. Again, not looking for the precision, but they served their agriculture market very well. Oh, that's right. Hemisphere was just bought by Case New Holland. This is going to be interesting. That's all I'll say about it. It's, good for both of them, actually. Yeah, as I talked about earlier, and I get asked a lot by users, and I'll be right up front with a network user. You bet single base is going to beat the pants off a network under certain conditions, but it's very conditional. And then there can be a reverse situation going on. RTK accuracy PNG. I can't open it. But anyhow,
Gavin, yeah, this is Michael. So, in trying to stay very, I guess, manufacturer specific, but I was really impressed. Rob Green did a presentation of the 7 states, and I've referenced it a couple times. The one thing that apparently Trimble Centerpoint RTX does real time with that SBAS solution is it does that transformation between ITRF and NAT83, and it also does an HTTP transformation as well, real time, along with the orbits and the clocks. And it seems like it's really amazing. The presentation there, although he was that manufacturer's representation, says he thinks that all the survey grade receivers are going to kind of follow suit with the SBAS based real-time PPP. Anyway, I'm probably getting ahead of your presentation, but
no, that's a good point. And yeah, I actually think that fast PPP and a hybridization will be probably what we're all using in the future. Networks will mainly be for geodetic purpose and to provide the tighter modeling that fast PPP needs. Actually, our network, there's a bunch of PPP providers that lease data from us for that purpose. And they're not competing because they can't hit survey grade. And about the the transformation that they and others do between the NAT83 and the ITRF, it still doesn't match in places like on our coast where we have the high velocity. It doesn't match. Yes, they're doing it, and they are doing HTTP, but HTTP is not as refined yet because they don't have all that isostatic data, the NGS, so when we get to the 2025, the NatRef 2022, which is going to be like 2025 or 27, that is going to be modeled very, very well. And also they will be nearly coincident when it first starts. Will be essentially on ITRF, but with a fixed plate, with a plate fixing. So at that point in time, all of our issues with the difference between PPP and NAT83 will go away on our coast. Inland in our state, they're spot on with that transformation that they and others do in the HTTP. But I just want to give people a caveat that depending on where you are in some of the wild and woolly parts of California that move like crazy, you may see a difference. but a localization will fix that. So, yeah.
Interesting. Well, yeah, we're moving all the time here, but we're still doing original surveys. So we aren't at that level of California.
Yeah. Oh yeah. You know, I used to survey in Alaska decades ago using Doppler and terrestrial observations, but okay, so yeah, single base kicks ass. Yeah, if you can see the base, that you can't beat it. If it's a site base, you can't beat it. You got to resolve your own geodesy. You got to make sure it doesn't get stolen or run over, but that's okay. Less than a kilometer, you can pretty much beat network RTK. It's not that it's a dramatic difference. And when it's a site base, your vertical is going to be better. Now, within radio range, you bet, because you're within a few kilometers or miles. Absolutely. 5 to 10 kilometers, they start to hit about par on each other. And past 10 kilometers, it degrades. Now, you can have a good iono day, and you can fix to your base could be 70 kilometers, 100 kilometers. I've fixed between Seattle and Spokane for fun, or Seattle and Portland, just for fun. Not advising anyone to do it, but it's very conditional. The thing about single base is, and if it's a site base, boom, okay. But if you're going to mix and match bases, you could have on any given day, you could get different results if it's longer baseline lengths. And that can really mess you up, as a construction company here found out, because one of the permanent bases went down, and when they grabbed another one, everything went out of whack. If they had started with the network solution and based it all off that, it wouldn't have mattered if one of the stations had gone down. So yeah, now your base and rover antenna, your receiver and antenna have to be of equal or better quality. Your base does. The base has to see much more sky, or at least as much as the rover. And the base supports same SAT signals as the rover. I keep seeing people in forums saying, yeah, I'm going to buy one of the new rovers and use my old one as the base. Well, you're not going to support all the signals. Can't do that. And if the base doesn't get stolen or run over or assaulted by some animal. I want to give you an example of where degradation over distance. So this is the same receiver in that cluster over on the left, the big spread out one. That is a 16 kilometer baseline to a base. Doing single base, full constellation, whole 9 yards. It's top quality, clear sky. That's what I got over a 24-hour period. That tiny little cluster right around the zero, that's a VRS solution over 24 hours. The nearest base is 16 kilometers away. Yet it's using the strength of modeling from 9 other stations around it. That's where the difference can be made. But then again, if you got a site base, that's going to beat it all. So that's the end of my prepared stuff.
Mhm. Great as always. That is lots of moving parts there. Does anybody? I had one question from somebody who had emailed me, but if anybody wants to get the questions rolling for Gavin, we can get going. Anybody want to unmute and ask a specific question? George is typing away already. Nobody? Let me, so the one that I got emailed, he wasn't able to jump on tonight, but so he teaches his clients to run the PPK with their drone flights to a known position on their site. But we've had 2 issues that plagued this workflow lately. The client forgetting to enable the static file and realizing it when the flight is over, or the batteries on the rover or base die before the flight is completed. So the question was, and we talked about this before, but the question is, can we create a Rhinex file back in the office for a given lat and long on the site with the start time and an end time frames with 20 minutes on each side with 1 second intervals needed for PPK. And so his words with this would be a game changer if this actually exists. So
yeah, there's actually, it's called virtual Rhinex.
Okay.
And different RTN software manufacturers have this under different names, but I'll call it virtual Rhinex. So what it is when you got a group of stations out there and they are network processing, they're actually taking all that data in from the stations in a network. Our state, we break it into 6 pieces because of velocities and tropospheric scaling, but it takes all of those and it's processing them all the time. And when you ask for a custom correction, it knows where you are and creates that virtual base and it gives it to you. Well, it's storing all that data. And it's storing all that data, which is a massive amount of data. So we don't keep the data for more than a few days because we blow up every server we could buy. But that means that you can go back, put in a lat long, it doesn't have to be exactly right on a known point. You can put in a lat long roughly in the middle of your job site and put in a window and it'll create the virtual Rhinex, which is exactly what it would do with your virtual solution, but it's making a static file out of it. And that's come in handy for drone operators. Quick note about drone operations. And this is feedback from users and doing my own stuff. So, the way to use GNSS with your drone is, okay, well, if you go up and put down ground targets, you want to be super precise and you put down ground targets and you do a GNSS campaign and get really precise, run a digital level through them, maybe close traverse, whatever. You're doing that and you're using targets. And it's arguable that that's the most precise way to do something, if not, maybe not the most efficient. The other way to do it is put your own base up. And actually, that's that short baseline length is a huge plus. If you have a base on your site and you're recording it, you can post-process the PPK with it, which mixes in the IMU. And that's fantastic. The other way is to use the RTK from base. The RTK and PPK are essentially doing the same thing, but with the PPK, you can add precise orbits later, little things like that. You can process it forward, back, forward again, like with mobile mapping and get a little bit more out of it. But some people just rely purely on the RTK from a base on the site. And most of the drone companies can sell you a $1,200 base, which is basically a U-Box chip in a box, which is the same chip on the drone. So it may not be the best quality in multipath and signals and things, but that's great. Others will go to their local network and they'll go, oh, I'm going to single base. But if that base is 5-10 kilometers away, it's not as good as the base on the site. Or a VRS. Well, okay, for the longer baseline lengths, it might be a plus. But you can do virtual Rhinex and do the full PPK, which is getting you back into a little bit more reliability of the solution. So the virtual Rhinex is if you have a network somewhere where you're at, ask them about it. Ask them if you could try it out. I'm starting to see a lot of drone operators using that in our area. So.
Okay, cool. Perfect. I'll let Mike know. He can jump on there and watch that. Schroeder had wanted to add on too.
By using PPP and deep vegetation cover with high multipath.
Yeah.
Well, okay, let's disconnect that. Using any GNSS in heavy vegetation with high multipath. Well, a big plus study in Japan they did for their forestry industry. They found out that the coolest thing was to get that antenna up higher. And I found out when I put an antenna up on a 15-foot rod in these great big thick evergreen forests here, it did help. But GNSS in thick vegetation with high multipath is multi-constellation is a plus. Now about PPP, if it's real time, getting the PPP from the geostationary satellite over there, the equator, that's your killer there.
Yeah.
Yeah.
Well, I just wanted to share experience. So I told you, I started playing with that Nav Canada clock corrections and precise ephemeris. And what was unique with that is that it delivered a solution. They had a little software that ran it epic by epic. And so the case that I said is like, we had some just terrible. I mean, you shouldn't GPS there. You can't hardly see daylight in Southeast Alaska, huge trees, 200 feet tall. Well, just let it run and cook, a couple hours of dual frequency data, run those corrections. And then we would create basically like your little scatter plot that you showed, Gavin.
Yep.
And so here are all these wild cards, and they're all over the place. It could be meters or tens of meters, but with enough time, epic by epic, I mean, we would throw it in a spreadsheet and then do a scatter plot. If you had those signals that all came through without multipath for one epic data was as good as long range. This is all post-process stuff. So, yeah. I mean, it was very costly to get in there, and to like traverse through the trees would have been days worth of work, but 2 hours of data and play with it with just those corrections, because it's independent. And if you had clean satellite signal and you applied those corrections with enough data, looking at, a smattering of maybe 100 epics over 200 hours of data, but it was all hitting that bullseye. Anyway, we put the bank, we tested it, of course, the proper thing, running those traverses in. So it's just a gray hair thing that we realized that looking at alternate ways to process your signal other than manufacturers, software that wouldn't do a static baseline from 3 kilometers to that data set because it's full of cycle slips and garbage multipath.
Oh yeah. PPP is just astounding, and post-processing is where you can squeeze a lot out of it. And then Trent, so last week I got to visit JPL and I was interviewing folks working on quantum sensing. And one of the type things about quantum sensing is what it could do for a GNSS antenna. It could really make, moot all of this hand wringing and posturing about, manufacturers posturing about besting canopy. It could be astounding, but I think we'll all be retired before that really hits. But no, I'm thinking about 5 years, you'll start to see quantum sensing and GNSS receivers. But anyhow,
that's where I was just about to ask, since we were on this topic, what's kind of coming down the pipeline? Because that was okay. Vegetation overheard cover. What the key that Pat chimed in on the chat there. Key producing. I was just gonna, while we were on that topic, is what's going to start penetrating that, because wasn't that kind of the thought behind the L5 coming out, was going to be able to penetrate some of that stuff as well? Or
yeah, so the L5, I kept hearing people saying they weren't going to buy a new rover until L5 was completely here. Well, the thing is, L5 is in the other constellations. The E5s in Galileo, and there's multiple flavors of that, is already here. The B3 of Beidou is like L5 on steroids. It's already here. Eventually we'll have it on all the GPS satellites. More modern signal, more refined, a little bit of power, increase, but third signal processing, fourth signal, fifth signal processing, just it becomes mind blowing what it can do. And I remember out, getting a demo of a rover under a big tree, and they said, here, I'm going to turn on B3. Boom. Just that one extra signal made all the difference. Wow. And all those extra signals can be used in post-processing too. So anyhow, I better let you guys all go.
No, yeah. Go. Did anybody have anything else on it? They want to be be cognizant of Gavin's time. Did anybody have another question or anything they want to ask?
Yeah, Pat, I agree with you
Okay.
about quantum sensing. It's blowing my mind, and just for GNSS antennas, for detecting underground utilities, quantum sensing for surveyors is going to be a big thing.
Interesting. Okay. That's good to know. Good to follow that kind of stuff coming out.
Yep.
Well, I appreciate it as always, Gavin. And
Cool.
I think everybody got a lot out of it. As always, there was a bunch of comments on there. So we appreciate your time. And have a great night. Have a great week, everybody. And
Oh,
we'll be back next week.
hi, Kevin. I need to ask you about something. I'll call you later in the week. Take
There
care.
you go. Perfect. That's awesome. All right, everybody. Have a good night. Bye.